So hello everybody, my name's John and I work in the structure elucidation team here at Pfizer in Sandwich. And today I'm going to give you a bit of an overview of who we are and what we do. I'm going to run through our typical workflow for structure elucidation. And I'm going to talk about a couple of interesting anecdotes from case studies that we've seen over the last couple of years. So firstly, who are we? So I'm a member of the Structure Elucidation Group here at Sandwich, and we're a part of the Analytical Research and Development, ARD department. Now, ARD's role is to develop and execute the analytical chemistry needed to ensure that medicines we produce are safe. These might be methods to detect impurities in API, drug product, intermediates, or excipients. And these impurities could be degradants or process-related impurities. We're also responsible for developing control strategies and specifications for these impurities, and we're responsible for designing and performing the stability studies and subsequent modelling of stability data, which are used to underwrite a medicine's use period, and many other analytical activities. So the department is split across multiple sites, both here in the US, and the Sandwich site here we mostly deal with products in phases 2 and 3 of the drug product development life cycle. So the Structural Elucidation Group, of which I'm lucky enough to be a member, there are two Structural Elucidation Groups, one here in Sandwich and one in Groton in Connecticut. And our main role is to support the ARD department by elucidating unknown impurities. And this will typically take the form of an analyst coming down to us, waving a chromatogram at us, which will have a great big peak for the API, which we tend to refer to as main band, and a tiny little impurity peak, and they'll point at the impurity peak and say, what's that? The chromatogram could be of API, it could also be of intermediates, and the impurities might be a PRI or a degradant. There are other activities which we're also responsible for in SEG. There's filing documents, so documents for regulatory bodies showing that the drugs and impurities are what we claim them to be. We will do support synthetic chemists, so they might come to us with samples if they're not sure if they've made what they think they've made, or if they're having difficulty determining which stereoisomer or regioisomer they've made. We also support our colleagues in materials characterization team. So if they have problems with what are the black specks or white lumps or pieces of plastic they might have found in a starting material. We might help the parenterals team with what are these precipitates that are forming in my injectable drug product. And we also might have questions along why is a batch of API yellow or green or brown or red when it should be white. So most of the problems we get we'll address using a fairly typical structure elucidation workflow. What we will tend to do is use the project's chromatographic method to collect usually electrospray mass spectrum. We'll collect this across the whole chromatogram with very accurate mass, typically better than a millidalton. And we'll use this accurate mass to determine possible formulae of the impurity. We'll base the possible elements on the molecular formula of main band and some chemical common sense. We'll also use the isotope pattern of the mass spectrum of the impurity to narrow down the list of possible formulae. And by comparison of the proposed formulae for the impurity and with that of main band, we can tell us the nature of the chemical change. So we maintain an ACD spectrus database of impurities for all current and past projects. And these can be searched by molecular formula, molecular weight, M/Z value, or NMR peak. And this database contains structures and any spectra, both MS, MSDN, and NMR, for any compounds worked on by SEG, as well as metadata, including ELN references or synthetic root step. And this allows us instantly to check if somebody has worked on a particular impurity before or a similar structure, and if similar fragmentation has already been seen. And this is very useful for the group because not only do we all work on all the projects that are currently in the shop, but we're also split across 2 continents. So it means rather than having to email around and say, has anyone seen an impurity in danuglipron, molecular weight 347, you can actually check the database and see if somebody has seen this impurity before and save yourself a bunch of time and effort. However, if an impurity that we see in the LCMS isn't already in the database, we'll then go on to record MS spectra of the main band and the impurity. We'll assign the MSMS spectrum of the main band, or we'll look at the assignments that are already in the ACD database and compare those with that of the impurity. So this can tell us where on the structure any changes have taken place. For example, if you had an impurity that was an oxygen up on danuglipron here, say, then you could look at the fragmentation scheme and see which fragments were 16 heavier than the MSMS of danuglipron and isolate where on the structure this extra oxygen occurred. Often this, with a bit of chemical common sense, is enough to assign a structure to the balance of probability. Now, many seg jobs don't need anything more than this balance of probability assignment, but sometimes the data is too ambiguous to propose a structure or definitive proof is needed, in which case we'll move on to NMR. So NMR requires purish samples, and these can either come from a chemist who synthesized it or from isolation of an impurity. The more abundant the impurity is, the easier this isolation step is, so samples with enriched impurities, i.e. forced degradation or mother liquors, are our friends here. So proton NMR can sometimes give a proof for structure on its own, but more usually we'd use 2D NMR techniques, usually proton detected, to give correlations linking parts of a molecule together. Now, here an example of some of the 2D experiments we might use, ranging from a standard proton 1D experiment, which we could probably get away with 10 to 50 nanograms of material to pinch, all the way up to an inadequate or a direct detect 15N experiment, where you're going to need a teaspoonful of material and a shed load of luck. So we will usually process these spectra in ACD. This allows much easier assignments, particularly for complex or impure spectra. I'm old enough to remember the days of assigning spectra with a pen and paper, and I would not go back there. We had a project in a few years ago where the API had a molecular weight of 1500, which meant that we had imps we had to deal with a 3000 molecular weight, and doing that by hand would just not have been feasible in any sort of reasonable timescale. So we always use ACD for the spectral assignment. So having assigned the spectrum and hopefully worked out what the impurity is, we then will compare the measured carbon-13 chemical shifts of the impurity with those predicted using ACD's CNH predictor module. We do this as an essential sanity check and a nice unbiased check to make sure that we're not making unfounded assumptions about our structure, completely barking up the wrong tree, or we've not just made some sort of daft human error mistake. And once we've checked it against the CNH predictor predictions, the final structure is then reported to the project analysts or chemists with any appropriate caveats. The structure and spectral data are then added to our ACD spectral database. And this is now a button click process thanks to ACD's automation scripts. And in the case of NMR data, these data are then added to the training set that's used for the ACD CNH predictor module I mentioned before. And this has the advantage that when you've got a few similar structures for a particular API in the database for the training set, it means that the predictions become more accurate. So for example, over the course of 2 years work on danuglipron, the RMS errors for 13C NMR predictions went down from 2.5 ppm down to 0.2 ppm, which is not too shabby at all. So I'll now go into a couple of case studies where I'll talk about some examples of this workflow being applied. And the first one is a mass spec problem we had, which is about a +1 Dalton impurity in danuglipron. It's what? So this is danuglipron here. If I just get my pointer up. Yeah, this is danuglipron here. And the project had a problem, danuglipron. And that problem was this shoulder on main band here, which had appeared when they tweaked the chromatographic method for improved separation anywhere. Now, peaks poking out from under main band are a concern because it suggests there's an impurity in the medicine that we've hitherto known nothing about, and this is a bad thing. Normally, great efforts have been undertaken earlier in the project so that this doesn't happen. So even though it's only present at 0.02%, which is a very low level, it was important that we look at it to work out what it is and to work out if it's real or if it's a chromatographic artifact caused by fronting or some other problem with chromatography. And if it is real, what is it and how worried about it should we be? So we went to our usual first port of call, which is positive mode LCMS. Now here you can see the mass spectrum for main band at the top and the impurity at the bottom. And straight away you can see that these differ by 1 Dalton, so 556 for danuglipron, 557 for the impurity. So this is telling us immediately that the shoulder on main band is indeed chemically different to danuglipron. So it's not just a chromatographic poor peak shape. Now, at this point, anyone who's done any structure elucidation is probably immediately thinking it's gone up by 1 Dalton, it's an oxygen replacing an NH. However, if you look at the structure here of danuglipron, there are no obvious places on that structure where you could replace an NH with an oxygen. And furthermore, if you work out the accurate mass of an oxygen for NH replacement of danuglipron, you get a formula of 557.2195. And this is miles away from the 557.2420 measured mass. And given that our Orbitrap is generally giving mass accuracy of better than a millidalton, it clearly cannot be this modification. So we use the formula generator tool to generate possible molecular formulae based on what we thought a sensible molecular elemental composition of an impurity in danuglipron might be. And that gave us this. And none of these structures, none of these formulae make any sense. None of them are the sort of things you would expect to see from chemical modification of danuglipron. So we moved on to the next stage in our workflow, which would be MS-MS. Here we can see the assigned MS-MS spectrum of danuglipron at the bottom and the impurity at the top. And remember again, this impurity is chromatographic separated from danuglipron. And you can see the fragmentation between the two is very similar with many of the same ions. However, there are a few ions like 325, which are 1 Dalton heavier in the impurity peak, and there are some are unchanged, like 215, and there are some like 190 and 281 that exhibit both the same ion and 1 Dalton heavier. So in an effort to try and identify what was causing the 1 Dalton mass difference, we looked at the 191 fragment and put that through the formula generator, and again got no sensible formulae when we used the sort of elements that we were expecting to see. So at this point we started getting a bit desperate. So somebody said, what if it's deuterated? So we put deuterium into the formula generator and immediately got a sensible formula, which was only out by 0.04 millidaltons. So what this means is that the deuterium, so for example, for this fragment here at 190, the 191 differs from the 190 by only a single deuterium. So one of the protons has been replaced by a deuterium. And even more interesting is that deuterium is only present in very specific fragments, suggesting that deuterium is localized to a particular moiety of the molecule. So using this MS-MS, can we figure out which moiety of the molecule contains the deuterium? Yes, we can. And the giveaway fragmentation is here, this 281, 282, and the 148, 147 pairs. Now these are caused by fragmentation of the piperidine group along here or along here. And they show unambiguously that deuterium is only present at this position here, alpha to the nitrogen of the piperidine ring, and nowhere else. So this is not something we were particularly expecting. And consulting my colleagues within the department and the rest of the SEG group, none of them had seen anything particularly like this either. So given that I hadn't seen deuterium isotopomers separated by LC before, and none of my colleagues had seen it before, we had a trawl of the literature to see if there was any precedent for it. And we found a couple of papers, one where they'd seen separation of the deuterium isotopomer of ulpristal from ulpristal by HPLC, and one where they'd shown it was possible to separate D3-benzapine from benzapine, again by LC. We also had a look back at the work we'd done on danuglipron analogues, and found that there, if you look carefully, you could see a 1 Dalton peak separating from main band. So why was this happening? We first off looked at conducting DFT models of danuglipron with and without the deuterium alpha to the nitrogen of the piperidine ring to see if it had any change to the conformation, and we found no change in the conformation. We didn't believe the difference was down to the mass difference in deuterium, because otherwise you'd see this effect all the time for all of the deuteriums in the molecule. Now, both with danuglipron and in the literature examples we have here, the deuterium is alpha to the tertiary amine. So we were wondering if this could be the thing that was causing the separation, and we were wondering if the deuteration had an effect on the pKa. Now, under normal circumstances, we'd use ACD's Perceptor tool for predicting the pKa of our analytes, and that works extremely well. Unfortunately, that's based on a training set, and for reasons that are probably fairly obvious, ACD hadn't chosen to screen large numbers of deuterated analogues of compounds to build this training set. So what we had to do was find another way of seeing if we could predict what effect the deuteration would have on the pKa of that nitrogen. So what we did was we looked at the pKa's of 30 tertiary amines from the literature, and we used DFT to calculate the Gibbs free energy differences between the protonated and unprotonated tertiary amines. We then plotted these Gibbs free energy differences against the literature pKa values for these simple tertiary amines. Now you can see here, for example, you've got N-methylpiperidine, which we decided we'd use as an analogue for the piperidine group in the danuglipron. Now, the model suggests that the pKa of this N-methylpiperidine should be about 10.4, and the experimental value is about 10. So this is good enough for our purposes. And we then went on to run the prediction again based on N-methylpiperidine with a deuterium alpha to the nitrogen. And we found that this increased the pKa of the nitrogen by 0.04 units. So this suggests that deuteration, alpha to the tertiary amine, slightly increases the degree of protonation in the material, thereby slightly increasing its polarity, thereby causing the deuterated species to elute slightly faster. Now, this isn't a big change in pKa, but we think it's big enough to describe the very small change in the separation behavior. So the conclusions of this study were that there's a shoulder on the front edge of main band, which was chromatographically separated, was a natural abundance deuterium isotopomer. So people have asked, where does deuterium come from? And the answer is the Big Bang. This is natural abundance deuterium. So it's normally present at 0.01% just in nature. And we saw the impurity at 0.02%. So if there are 4 possible positions for this deuterium to go in alpha to the nitrogen, that would give you about 0.04%. But with the accuracy of the integration on that peak on the front edge of main band, we think this is a reasonable explanation. The deuterium was replacing one of the hydrogens alpha to the piperidine nitrogen, and this is therefore not of concern to the project. Nobody's worried about deuterium isotopomers of your API. And the separation was likely a result of subtle increase in pKa for the piperidine nitrogen. So moving on to the second case study, this is an NMR problem that we were looking at, and this is structural elucidation of a ritlecitinib hump impurity. So ritlecitinib is an investigational JAK3 inhibitor for the treatment of alopecia. Now, early in the project, a broad hump peak was observed at very low level in an LC chromatogram of ritlecitinib. But this hump wasn't seen again in later batches. However, later on in the project, a much later batch formed a precipitate while it was being synthesized. And when this precipitate was filtered off and analyzed, it showed a very considerable peak here, which was in the same position and same shape as the hump peak that had been seen earlier. And this hump corresponded to about 25% of the total peak area. Now, the chemists were keen to know what this hump was, why it was causing precipitation, but the hump did not ionize in LCMS. However, a 25% impurity should stick out like a sore thumb in an NMR spectrum. So we dissolved the precipitate in deuterated NMR solvent and recorded the proton NMR. And what we saw was this, the NMR spectrum of ritlecitinib and not much else. So there are no obvious impurities in this spectrum. Now, those of you who are sharp-eyed might spot that there are rather more peaks in this spectrum than you would immediately expect at first glance for ritlecitinib. This is because there's hindered rotation around this amide bond here, which means that resonances for protons such as 14 here appear twice for the 2 conformers. However, even given this complication, there are no extra peaks for a 25% impurity. However, if you look particularly carefully at the spectrum, you can see that some of the peaks are slightly broader at the base. So could this slightly broad things under the base of some of these peaks be the impurity? And how might we find out if this is the case? Well, if the peaks are broad, it might be because they're of high molecular weight and are diffusing slowly. So we could use a technique called diffusion editing to try and remove or reduce the resonances from molecules which have relatively higher diffusion rates. So this would reduce the intensities of the API resonances and leave behind, hopefully, the broad resonances caused by slow diffusion species. So this works using a similar pulse sequence to that of Dozy NMR. What happens is you will do a 90-degree pulse to excite all your spins, and then you'll apply a dephasing pulse field gradient to this, which will move all the spins across the sample to different phases, which means that your net magnetization that you will see is 0. And if you then rephase these by applying a 180-degree pulse in the same pulse field gradient, you will get a signal back. However, if you try to do this with a species that's diffusing, the peaks, the spins will move along the tube, and when you apply the rephasing pulse field gradient, you will no longer get all of your spins lining up, and you will get no signal. Practically, as I say, this is the same pulse sequence as you use for Dozy NMR. And in practice, what it looks like is this. So this is the NMR spectrum at the top of the rituximab containing 25% of the broad hump impurity. And as you increase the gradient power, you find that the rituximab solvent peaks are suppressed, and you're left behind with this NMR spectrum of the slowly diffusing species. Now, it's not a very pretty NMR spectrum, but it still contains plenty of NMR data. So what you can see, for example, is that the peaks for 7, 2, 10, 8, and 9, which are from this aromatic region of the compound, are still present, as are a number of signals for the piperidine part. However, the signals for peaks 21 and 20, which are this olefinic moiety, have disappeared. So what we know is that the impurity is related to rituximab because it has many of the same peaks, that the aromatic region is still intact, but that this olefinic region has changed. So this suggests that you're getting polymerization through this olefinic region, that you're not getting the Michael addition polymers, and that therefore the structure of the impurity is this, and that it's a polymeric impurity. Once we know that we've got a polymeric impurity, this then allowed the chromatographers on the project to go away and develop a size exclusion method for the analysis and quantification of this impurity. And even better, they were able to then isolate some of the polymeric impurity on its own, and we were able to get an NMR spectrum of the pure polymeric impurity. And rather gratifyingly, the purified polymer NMR spectrum looks essentially the same as the diffusion edited spectrum that we used earlier. In fact, the diffusion edited spectrum is slightly clearer because we don't have solvent or water peaks obscuring some of the resonances. While we were working on the project as well, it was noted that some of the samples that were analysed on the size exclusion method gave polymer peaks of slightly different retention times. We were also able to use the same pulse sequence, the same technique to determine relative diffusion coefficients for these peaks and work out that the reason that peaks were coming at slightly different retention times was in fact that they were of slightly different polymer lengths. So the conclusions from the rituximab work was that diffusion edited NMR was able to be used to reveal a hidden resonance from a high molecular weight impurity. These resonances allowed elucidation of the impurity structures. Once the impurity had been ID'd, we could use size exclusion chromatography to quantify and control this impurity, and that we could also use the same NMR experiment to determine relative chain lengths of the impurity to see why we were getting peaks shifting in the size exclusion method. So finally, pharmaceutical analysis is a team sport. It's not an individual endeavor. So all of this work was done as part of a group. So I have to thank my colleagues in the Structure Elucidation Group who all did this work with me, Ruth, Drew, Rich, Teresa and Roland. The Daniel Glipron work was done with Claudio, Sam and Hannah. And Claudio was the chromatographer who developed the method. If anyone wants to know how good Claudio's chromatography is, he's capable of separating impurities that differ by 1 neutron. The ritlecitinib work was done with Mark, Almery, Griff, Rees, and the whole of the ritlecitinib chemistry team. And Mark was the chap who developed the size exclusion method. So speaking of it being a team sport, if you're interested in solving the sort of problems we've been seeing here and many others, then the department is expanding and we're hiring. And we're looking for people ranging from new graduates who want to learn from people like Mark and Claudio, who are the best in the business, to experienced analytical chemists of every flavour, from inside and outside pharma, who can bring their own skills and experience to bear on these and other challenges. So if you think this is you, then keep an eye on the website I've got there, because other adverts will be appearing soon. And finally, thank you for listening to me. And if you have any questions, please ask.